All right, here's our next unit. I'm going to talk about continuity and one-sided limits. Okay, now, first of all, we have a definition. What does it mean for a function to be continuous? There's a very visual way to see this, and you may have heard this before, but a function, if you draw the graph of the function, it's continuous if you can draw from left to right a complete function, or from right to left a complete function, without having to lift your pen off the paper. So here's an example of that. Notice it stays on no matter what happens. It stays, my pen stays on the graph. Now, a discontinuous function, we've seen these before. Examples might be coming up like so, point, it jumps up, continues this way, maybe heads up this way towards an asymptote, and then it comes back in this way somehow. Okay, so it goes in like that. So there are different kinds of, there's a hole here, different kinds of things can cause discontinuity. Here's a jump here, a break or a jump. And here is an asymptote, vertical asymptote. So those are ways, the only way I could draw this is to take my pen off the paper to continue the graph in either direction. I can't do it with one complete stroke of the pen. So now here's our definition there. 1, 2, and 3. These conditions have to be met. First of all, there has to be a point. Can't talk about continuity at a point if it doesn't exist. So it has to be defined. Second, the limit of the function as x approaches c, the point in question, that must exist also. Okay, so can't just have a point sitting all by itself and that's it. I'll show some examples, some drawings of what we mean by this, these existing and this being defined. And then the third condition, if the first two are met, if those two are met, then you have to check the third. Make sure that 1 and 2 are actually equal to each other. If they are, then you have continuity. So first question, is it defined? Second question, does the limit exist? Third question, do those two numbers match from 1 and 2? The values here and the value here, do they match? And if they do, then you have continuity. Okay, so let's look at some examples. We don't want to go to extreme cases, but if that's continuous on the open, if it's continuous at each point in that open interval. So if at every point we have these conditions holding, then we have continuity on an entire interval, open interval. We're not going to say what happens at the endpoints right now. Okay, but there is a notion of being continuous from the right and continuous from the left. If in a closed interval, we can have that. So that would mean that these, we'll have to talk about the left and right hand limits when we talk about that. But okay, now let's go back to example 1. Look at a couple examples here. So illustrate some of these ideas. Okay, so discuss the continuity of each function. Well, to talk about continuity, you have to talk about discontinuity. So, and here's a rational function. And from our experience, we know that this thing does not have a discontinuity anywhere except when the denominator becomes a 0. So to find the discontinuity, you would set the x, whoops, let's see, you have to set that x minus 3. Yeah. Let's get back in there. It's a little. X minus 3 equal to 0. So you set the denominator to 0. And then you solve it. So I'm doing it here. This is a simple x equals 3. So we know that this means there's a discontinuity here. We may not even recognize what it is, but we know that it's there because you can't have division by 0. Now, we just happen to know from our other experience that this is a vertical asymptote. Okay, so not only do we know that it's discontinuous there, but we also realize it's a vertical asymptote. So I might just say VA, vertical asymptote there. Okay, now everywhere else it's continuous. So we could say it's continuous everywhere. Continuous everywhere. Oops. Everywhere. I spelled that. Fix that. That's getting a little sloppy there. Okay. Everywhere except x equals 3. Okay, next one. Again, you see this. You look at the denominator, set it equal to 0. So we have x minus 3 equals 0. That means at x equals 3, we have a problem. We have a discontinuity there. So we can see it is also continuous everywhere. Except x equals 3. Now, what kind of discontinuity is that? That's also a good question, although we have answered where is it discontinuous. This one has what's known as a hole, and we'll be able to see that if we do this. Take that function and reduce it down to the equivalent function that's equal everywhere except -3. This divides out. You just get an x plus 3. So now when you look at this, this is defined at x equals 3. This is simple to calculate. But it means when this happens right here, this tells you that since the function is now defined at x equals 3, that means there must have been a hole at x equals 3 when that divided out. Okay, so the offending division by 0 is no longer present. Actually divided out. That means we have a hole. Okay, now the y-coordinate of the hole is simply the limit of this remaining function here, the simplified function, which is a 6. So we have a hole at 3, 6. That's what tells us. Okay, so whenever this happens, and the division of the factor occurs, and it leaves the factor missing from the denominator, it no longer causes division by 0, then you have a hole in the function. Okay, this other one here. Now, first of all, these are polynomials, and you should remember that polynomials are continuous everywhere. So really, since this is a piecewise function, really we're only concerned with whether or not these two pieces actually join at the same y value. That's the question. So when you see a piecewise function, you see that the domains are divided for each piece here. And at that division point where they separate, in this case it's a 0, do these functions equal the same number? That's the question. So if they do, then and that number exists, okay, then we have continuity. So first question is, that's the point in question, 0. What is g of 0? according to this, it's equal to 0 plus 4. That's this function right here. Then use this piece because this is the domain. And my value that I'm using here is a 0. That's in this set. So I use this piece, put it in here, and I get a 4. Okay, now, so that's condition 1. The function is defined at that point 0. Second question, what is the limit as x approaches 0 for g of x? Okay, that's our second condition. Does this limit exist? Okay, so let's go back over here. Oops. Does the limit exist? So the real question is, when it comes to this function, which piece do you use when you do this computation? And the answer is both. Okay, you use both. And so let's do that. Let's check out the first part. Does this, what does this equal? Well, it's equal to a 4. What does this equal? Well, direct substitution tells us it's a 4. So if a direct substitution works, then we don't have to think anything else about this. We've got x heading to 0. We get a 4. We get a 4 here. Now notice these two are the same, which means that's the limit. It's 4. And it also matches the value of the function. Now, there's something else in here that we should talk about, and that's when you have a limit of this sort, notice that when you're using this function, x plus 4, you're really only concerned with x is less than or equal to 0. Fact is, we're not even worried about the 0 in this case. Only the number is less than 0. Just remember, when you're finding limits, the limit point really doesn't matter here. The 0 doesn't matter. It's the numbers next to 0, close to 0. In this case, on the left side of 0. So we have a notation for that. This is what's known as a left-sided, or we'll say a left-hand limit. And it looks like this. You can say limit as x approaches 0 from the left. See the minus? It's in the exponent. And notice the evaluation is no different. You still directly substitute 0 in, and you'll still get that 4. But see, it doesn't make any sense to find. This is called a one-sided limit, and it doesn't make any sense to find a two-sided limit for a function at this endpoint 4, because it would be a different function. It would be this function as soon as you go past to the right side of 0. So it makes sense to talk about what's known as a left-hand limit for this case, and it's in general known as a one-sided limit. So you have left-hand limits and right-hand limits. When you look at this other piece here, you'll talk about a right-side limit or a right-hand limit. So let me show you how that looks. The right-hand limit. That would become, you would use this notation. The limit as x approaches 0 from the right side. See the little plus here? And you would be using this function. Valuation is the same. Do a direct substitution, you'll get a 4. Okay, now when it comes to two-sided limits, they only exist if the left and the right-hand limit at the same point exist and are equal. So that's how you calculate a limit at a point that's where you might have a discontinuity here. So we're not really sure. So we can use these limits to help us figure that out. Okay, so we have the two-sided limit. Let me just write that over here. Two-sided limit looks like this. Two-sided limit in general might look like this. Limit x goes to a f of x. One-sided limit looks like this. It goes to a, it might come from the right, or it might come from the left. Okay, now the two-sided limit will only exist if both the left and the right exist and are equal to the same number. Okay, so this will exist, will be equal to L, only if both of these are equal to L. So this is a way that you can check in case of these piecewise functions, whether or not you have an existing limit, and also whether or not you have continuity. Because remember, the continuity depends on the value of those limits. So now back to this one. We're trying to find the continuity here. So we have all conditions met. We have the function is defined at 4, and the value is 4. Defined at 0, and the value is 4. G of 0 is 4. And we also have the two-sided limit equal to 4. Okay, two-sided limit at that point. Now we needed to check these one-sided limits to make sure that happens. Okay, because they might not agree. And we'll probably see an example or two where they disagree, but for right now, we have continuity for this function. It is continuous. So could graph it without having your pencil leave the paper. Okay, now, since we're talking about continuities, discontinuities, we have two types. We have a removable and a non-removable. Okay, non-removable is if you have a function, you can't redefine it at more than a finite number of points. Okay, otherwise we would consider the function to have non-removable discontinuities. Okay, function can't be redefined or defined at the discontinuity without changing the function at other points as well. Removable discontinuity is you can alter a one or more finite number of point values for the function so that you can have the conditions of continuity met. And then the original function remains intact. You don't have to change an infinite number of points to make this happen. A finite number of points can be changed to achieve continuity. That would be called a removable discontinuity. Now we see this with holes. Okay, that's our main example of that exhibits this removable discontinuity phenomenon. So, excuse me, then the non-removables are, say, a vertical asymptote, VA. You could also just have a break, possibly, in the function, where you have a break or a jump, you might say. Those can't be removed. You'd have to change entire intervals of points, infinite number of point values for that to happen. So we wouldn't consider that removable. You don't want to change the nature of the whole function. That wouldn't be fair to the function. Okay, so let's look at another example here. Let's find discontinuity for this function and answer the question, is it removable? Well, remember, where do you look for discontinuities? In the denominator. Okay, denominator. So we have x squared minus 25 equals 0. Well, we can see that that will happen at x is plus or minus 5. We can see that. And okay, so we definitely have discontinuities there. Question is, are they removable? Well, let's take a closer look at, so what are they though? These are, it's definitely discontinuous. Discontinuous. Whoops, continuous here. But the question is, removable or not? Removable. Well, that we have to go back to the original function to answer that question. So, and we would do this. We would simplify by factoring if possible. Because notice that when you try to evaluate f of 5, you get 0 over 0. So that tells you something funny is going on. And when you try to evaluate f of negative 5, you get negative 10 over 0. Now that is definitely undefined. There's no question that this does not exist here, and it's undefined, therefore discontinuous. Or well, we know it's already discontinuous, but it's not going to be a whole. Not a whole. This one might be a whole, depending on if we can make that denominator become non-zero when x is a 5. So let's see what happens there. Again, working on this function, we see this reduces to 1 over x plus 5. So now this is the function that agrees with the original function at all except one point. So now since that divided out, that does tell us there's a whole. Okay, that tells us there's a whole because of that division. And a whole is what we would consider to be removable. Okay, wholes are removable. This is not a whole over here. This is actually an asymptote, vertical asymptote at negative 5. Not a whole. This is a vertical asymptote, VA. That's what happens for rational functions when you have a denominator equal to 0 and numerator not simultaneously 0 to the same multiplicity. You end up with that vertical asymptote. Okay. So x equals negative 5. It's not a whole. It is vertical asymptote. Vertical asymptotes are not removable. Okay. This is non-removable. Wholes, they are removable. All you have to do to remove it is to look at the limit here, which would be 1 over 10, and define the function to be 1 over 10 when x equals 5. That would remove the whole. Now, we usually don't have reason to do that ourselves, but you could create a function that would be a patched up function, but it would be a piecewise function. So we don't usually do that, but we will see them in examples. Okay, so they're good ways to exercise your knowledge of the concepts, piecewise functions. So now this one, the discontinuity for this function, let's discuss that. This one, it pays to have a little graph in front of you. Now, let's see, the point of question is, again, you have these intervals. Now, this is a strange way to write an interval, but we know that that's the same thing as this. This is, okay, well, let's write this one. This one's a little bit easier. This is just x less than or equal to pi over 2, greater than or equal to negative pi over 2. And this region, this interval is the rest of the number line. So this is x greater than pi over 2 or x less than negative pi over 2. So if you put these two sets together, this one and this one, you'll see that they encompass the entire number line. So we have a couple places here where that are in question, whether or not we have continuity. So let's take a look at the graph of this portion here. Let's take a look at that. That's a sine function, but it's the absolute value of the sine function. So now let's put a quick sketch together. Normally the sine function does this. Okay, and it also does this. And at pi over 2, it's a 1, so that's a question. So we would stop it right here. And right there. In other words, at pi over 2, and this point here is negative pi over 2 on the x-axis, and this is a negative 1, a positive 1. And that's normally the sign between these two numbers. However, you're going to take the absolute value of the sign. So what we want then is change that color. Let's make it blue. So what we're going to see is this. Just that in the middle. So it's kind of like a V, a script V. Looks like that. Okay. Now, the rest of the function is this function here. It's just an x. So we got some real problems on this one because x, let's begin it at pi over 2. Well, when x is pi over 2, so is y, because y equals x. So that comes in up here. This is a 2. And pi over 2 is about 3.5. Sorry, 1.5. It's about 1.59 something. And so it's in here. That means the function starts about here. And it starts with a hole right there. And it heads up. Oops. The hole disappeared. There it is. Okay. It heads up to here. Just like that. That's the line y equals x. So it's up there at pi over 2. And then the bottom on the left side, in other words, this part over here, now it starts down here at about negative 1.5. So there's another hole here, and then like that. So, I mean, this is just a line if you wanted to show the whole thing. Let me just pick another color here so you can kind of see how this comes through here. It just kind of connects. I mean, that's the line y equals x, except there's this little blip here in the middle where it becomes this function. So that's what we're seeing in here. And you can see that we've got some discontinuities here. I mean, without a question. We couldn't graph it without seeing these. So those are the points in question. There are 2 of them, negative pi over 2 and pi over 2. And we don't have a lineup here of these functions. So another way you could show that without actually drawing the graph is to find those limits. So for instance, just to show you how we can use the new ideas of the left and right hand limits, we can say, let's look at limit as x approaches x approaches pi over 2 from the right. Whoops, that's, I fixed that. Why did I do that? I don't want that. Not right there. Okay. x is heading to pi over 2 from the right. So in other words, we're heading along the graph right in here, coming down this way. And you can see, so that would be using this function here, x. Well, a direct substitution tells us that that's just going to be pi over 2. So the limit actually equals pi over 2. However, notice that if you were going to evaluate the function at pi over 2, in other words, g of pi over 2, it would come from this bottom piece, because that's where it's defined down here, you see. And we would use sine pi over 2 like that, which we can see is a 1. So already we see that the limit from the right does not equal the function value at that point. The limit from the right does not equal that value. So we can see algebraically here, we've got a discontinuity. Even if we didn't have the graph in front of us, we could see this. This is a problem. We don't have conditions 2 and 3 met. I mean, the function does exist there. Okay. The limit exists, but it doesn't equal the function value. Okay, so number 1, g of pi over 2 does exist, yes. Number 2, the limit from the right, at least, we saw that. We didn't even have to calculate the limit from the left, because we're saying already that the limit from the right of the sine of x, or sorry, whoops, not the sine of x, the x, we're working with x, equals a pi over 2 for that. But the problem is g of pi over 2 actually equals a 1. Okay, existence equal 1. So third condition was that 1 and 2 were equal to each other, and we can see that they're not. 1 and 2 not equal. So you can see how this fails to meet the conditions of continuity, the definition of continuity. So 1 and 2 are not equal. So that's how it is discontinuous there. So you could show that all of this work algebraically, and I just want to tie it in with those concepts. Now, that you would also see that the two-sided limit here does not exist. If you were going to calculate this for g of x, it does not exist. And the technical reason is that the left limit, the left-hand limit, and the left side limit does not equal the right side limit at pi over 2. You could say that just outright. That limit doesn't exist because of that. So, I mean, the left one, left side limit, would be this limit x approaching pi over 2 from the left, and you would have to be using this function. We can see that that's actually equal to a 1, and the limit x goes to pi over 2 from the right, you'll be working with this function, that piece, and that's equal to pi over 2. These numbers are not equal. Okay, so even if I didn't have a graph in front of me to show me this huge gap in here, I could see from here that since these aren't equal to each other, that two-sided limit does not exist. So two-sided limit does not exist. Since we have a problem with the left side, left-sided, not equal to the right-sided. So there's a lot of reasons why this could fail to exist, but this is one of them. Okay, it might also fail to exist if one of these didn't exist, if the left side didn't exist. then we couldn't have a two-sided limit. So they have to exist, and they have to be the same in order for the two-sided limit to exist. So both have to exist, and they both have to match. Otherwise, you have non-existence of that two-sided limit. Okay, so here's kind of a summary of this stuff that we just talked about. These one-sided limits. Limit from the left. It looks like this. Notice the form. And limit from the right. Notice this is C plus in here, which means x is coming to C from the right side. Okay, so limit from the right. And now also these are technically these are good ways to find behavior functions at endpoints. For example, in this function down here, number 4. Okay, so you have finding the limit of the square root of this. Now, this is as x approaches 3 from the left. Now, from numbers less than 3. Okay, now notice it wouldn't really make any sense to try to find any other kind of limit here. So it's almost implied that even if you wrote x going to 3 as a two-sided limit, it really only includes this left side limit, because if x is bigger than 3, then you have an imaginary number. So it's kind of implied that you're saying you must use a left side limit. So now what does it equal? Well, we do a direct substitution. Just throw that 3 in there and see what you get. Okay. So our function, our limit is equal to 0. What is the function value at 3? Well, it's the same. 9 minus 3 squared is a 0. So we do have continuity there, and we do have a limit does exist. It's only a left side limit. And graphically, what we're talking about is this 1, 2, 3, 1, 2, 3. It's a semicircle like that. And we're examining this limit on the right. It's right here at this point. And as you can see, it's a 0. On the graph, it's a 0. And that's confirmed with our work here, finding these limits. And find the function value here, f of 3 is 0. Okay, and notice the domain for this function is only between -3 and 3. So we don't really have any values to the right here or over here. Okay, so that's really just, we want to talk about that and some of the definitions in this context. So, okay, now here's another one. I think I'm going to cut this at this point, because this video is getting kind of long. We'll pick this one up on the next round. So it'll be a part 2 for this one.